Hi, everyone. My name is Hossein Kabir. I'm a PhD candidate in Construction Materials Group at the University of Illinois at Urbana-Champaign. So what is my PhD research philosophy? So when I started my PhD in September 2020, 4 years ago, the first thing I noticed in my campus was the saliva test for COVID testing. This test had 4 main elements. It was rapid. It was not super rapid. It was like 24-hour testing. It was affordable. I would say it was reliable. And compared to the nasal testing, which is a bit painful, this test was much easier. And that's why after a few months, UFI got FDA approval on that test, and the whole campus was using that test for a year or two. And there are many other examples in life. So pregnancy test is one of them. So I used the same 4 elements to design sustainable and durable construction. So why is concrete durability important? Because it can cost human life. So 3 years ago, the Florida building collapse cost 98 people's life. And what was the reason? It was the ingress of water. Basically, water from the deck constantly seeped into the garage area under the pool and causing corrosion. And then the building collapsed. And there are many test methods in ASTM to characterize the transport properties. One of them is permeability tests. And I'm pretty sure many of you have used this test. Diffusion test, and finally absorption test. So all of them are useful. I'm not criticizing any of them. They can be combined to give us some idea. But the first 2, if you look at the apparatus or the equipment, they can cause error for many reasons. The last one, you just coat all the faces except the bottom one, and the sample touches water, the dry sample touches water, and it absorbs liquid. And we measure this absorption as a function of time. That's called absorption. It's well explained in ASTM C1585. And also, it's purely based off capillary suction. There are some theories, people say that there are different mechanisms, but scientists believe that this is purely capillarity. So let's talk about liquid flow due to capillarity. If you look at this brick wall, you'll soon realize that algae needs moisture to grow. And if you soak a paper towel in a dye solution, then why the dye solution rises? It's again, cellulose attracts water. So this is the experiment they showed us in high school. If all the conditions like the material type, the liquid type, everything is constant. But if you change the diameter of the tube from left to right, the capillary height increases. And the corresponding equation is here. It says that the height is 2 sigma cosine theta over g rho r. And the sigma is the surface tension of liquid. R is the radius. And g and rho are gravity and density of water. 2 variables are here. Theta, which is a contact angle, and r is a radius. So the capillary height is controlled by R and theta. So that was my initial thought during my PhD. What if I place a single water droplet on the surface of cement paste and see if I can indirectly measure porosity in the cement paste, right? So that was my initial thought. So this is like the geometry of liquid absorption in ASTM test. And then this is the first, like the diffusion equation, the one-dimensional diffusion equation, and knowing the initial and boundary conditions, like the sample is initially dry, the saturation is 100% here, and the flux or flow rate on the top is 0, then we can estimate penetration or cumulative absorbed water as a function of square root of time. And S is the slope of this line, which is called sorptivity. So if the S value is higher, that means our matrix is porous. That means it's more thirsty to absorb water rapidly. And I did this experiment on a bunch of cement paste substrate. From left to right, this sorptivity increases, and you can see in fraction of seconds, you can quickly capture the behavior of liquid, one droplet on the surface of a sample. So, and this work was published like last year. But what about concrete? This was paste. So this is something that I'm currently working on that. So this is like concrete. We have different parts. We have different regions. And water behavior can be different on different phases. So a few days before Sangmin left our office to Los Alamos, he helped me come up with this stage. So I built a stage. This is the XYZ stage. And if I look at the front part, we have a multi-channel pipette which dispenses liquid more systematically. And then the camera is like placed at a constant position from the pipette, so the image is always focused. So this is the bottom part of that, so the camera is viewing the sample, and then two informations are recorded. One is the displacement of the pipette, and one is the camera information. So this is an ongoing project, and hopefully I characterize concrete. But let's say this is you place a single droplet on the surface of cement. What I can capture is the initial absorption rate. What I cannot is the secondary absorption rate. And the secondary absorption rate is due to the slow dissolution of entrapped air in sample, while the initial is the initial capillary suction. So this droplet method can only predict the first one. So this shows I was able to predict the initial sorption in a matter of seconds, but I couldn't do the second one. Then how to do the second one? Then if you look at this brick wall, what you notice is the water level or the waterfront. This is what we call apparent water level. Visible to the naked eye, but we don't know if it's like the moisture corresponding to 100% saturation or 30% saturation. We just see a front of water. So if we look at this sample, water is absorbing, and you see the waterfront increases with time. And this is another sample, same thing's happening. So my theory is, what if you measure how fast the water level changes, and then use that information to predict the sorption properties? So instead of using the traditional way measurement, which is very tedious and time-consuming, imagine you do this test for 7 days. We just place 2 cameras or 1 camera, it's up to you. And then it analyzes the sample, and it captures the area ratio or water level, and then it combines it with the time. So how fast, if the change in water level is so fast, that means something is like the material is a bit porous. And then this video shows how by just looking at the image, we can combine the area and time value using deep learning to predict penetration as a function of a square root of time in real time. So the computer vision code, we wrote it from scratch, and it has input images, which is RGB images. It has segmented binary output. And in the middle, it has feature pyramid network, ResNet 50, regional proposal network. Also, we realized that if we remove this feature pyramid, if we remove this ResNet 50 and RPN, and if we solely rely on FPN, like we have bottom up and then we have top down, like downsampling and upsampling, we can quickly predict the water level. So one valid question is, I see this water level here. Does it represent what is happening inside of my sample? So I took my sample and I split it in half using a razor blade and hammer. And you see that on the split faces, the water level is comparable. So what about concrete? We couldn't use just water because we need like something to cut it. So I used dye solution. So this is the dye solution that came in contact with concrete. And after drying, like look at this sample, the water level is comparable to what we see on the outer surface. So this method is applicable to mortar and concrete sample. And apart from that, I also use cement paste mixed with different SEMs, clays, fly ashes, slags, even foam concrete. So this was the foam solution. And then even on masonry elements. So I cut this sample to 2 inches cubes. So these are the samples. And then I tested 7 commercially available masonry units, everything I could buy from Home Depot, and then it worked. So I was able to predict that. So it works on paste, mortar, concrete, and masonry. And also, if you're interested, you can scan this QR code that shows everything, like all the codes and how to install the packages and how to run this code and where to import and export the image. And also last week, this work was accepted in Nature Communications. So hopefully in 2 or 3 weeks, it will be available online. So this work was not possible without the help of my advisor, Professor Nishan Garg, and his group, my colleagues at Garg Group, and was supported by my civil engineering department. Thanks for listening. Any questions for Sam? We have time for
Hi, Hussein. It was a great presentation. In the initial part of your presentation, you put a slide with different test methods, and one of the test method was also NT-Bill 492, which is the non-steady state diffusion coefficient. I didn't understand because you are measuring more or less sorptivity, but that is the diffusion coefficient. Are you claiming that like this is a better method or something like that?
Okay. So again, here I'm not showing the comparisons of these methods. Definitely for diffusion tests, the test setup, the change in temperature, everything can impact the results. What I'm trying to say here is the third one, the absorption test, doesn't need any specific test setup. It's just you cut the sample, you put it in oven, or if it's like a paste, you soak it in isopropyl alcohol, and then after a few days you coat the surfaces and you get the absorption. The comparison of this is, I guess, well established in the literature, and that's beyond this.
Good morning.